Okay, so it's time for the change detection lecture. And change detection is kind of one of the more basic concepts, if you will, that you could imagine doing in remote sensing. But it turns out there's actually quite a lot of complicated things that you can bring into that equation. But ultimately, it's looking at the same location over two different snapshots or windows in time and looking to see what has changed from one time to the next and how we go about systematically identifying that. So let's talk a little bit about digital change detection. Biophysical materials, human, man-made features are dynamic. In other words, things change rapidly. Um, trees grow, grass dies, animals move, people build roads and houses. They may follow specific patterns or they may not, but they change. We also believe that land use and land cover change is a major component in global change and an impact perhaps greater than that of climate change. If you look back historically, where now there is a desert, there once were many thriving communities in the upper part of the Sahara. And where now there is a jungle, there once were ancient cities and roads and farmland in the Amazon. How we use the land and what land cover, in other words, the vegetative existence that exists, it changes frequently. Sometimes. Other times it remains relatively constant. There's been a lot of effort into development of change detection methods using remote sense data. I'm having some issues here getting my slides to. There we go. I thought for a minute the slides was never going to advance. So here we have Tunisia, and we're looking at from December 26th, the day after Christmas in 2004. And as some of you recall, that's when that tremendous earthquake hit, and it led to a tsunami of epic proportion. So we're looking at two different windows in time. Before the event, we have a really good, clear, cloud-free image from April 2004, and we have one afterwards in January of 2005. And you can see how in some places the change has been minimal, but in other areas where there were once beautiful beaches, they're now shallow offshore land. The beaches in some cases have eroded. The forest around the beaches are gone. In other places, the vegetation, the development, the habitation has all been stripped and the land left bare. Clearly, very different than what we see in the before image. So if we're going to look at this from remote sensing, let's look at some of the considerations. Successful remote sensing change detection requires careful attention to a couple of things. The first is your remote sensor system considerations. Certain sensors have certain limitations. They have certain constraints in terms of availability and how frequently they go over areas. Maybe it's not frequent enough. Maybe the areas have issues with, like, for example, cloud cover. Whatever it is, there are always things to consider relative to your sensors. Maybe you've got really good images from before from an older satellite, and now something happens and you're trying to compare, but the satellite's no longer working. So lots of things to think about. Environmental characteristics are also important. Some things, it doesn't matter whether you measure in the fall or the spring. Sometimes seasonality is important. Sometimes time of the day is important. Sometimes the position of the moon is important because of things like tides. Ideally, remote sensed data used to perform change detection is acquired by some sensor that holds all resolutions constant. In other words, it's not like it's jumping around, zooming in or zooming out. It's just a fixed assessment, so that's one less thing you have to worry about. Specifically, we're talking about not just traditional resolutions, but things like temporal, spatial, angle, the spectral, and the radiometric have all been accounted for. Looks like we're on a stall pattern again. Alright, so what are some of the system parameter considerations we need to think about? Temporal resolution. This should be held constant during change detection if possible. In other words, the time span that we're looking at, you want it to eliminate any effects of time. So if you're looking at something that happened, you want the time to be relatively close together, not, for example, looking at bare land after a forest fire and then comparing it to, for example, something in the dead of winter, and when all the leaves are off the tree and the vegetation numbers may look very different. Spectral resolution. Ideally, you'll want to look at the same sensor to acquire the imagery on different data sets. Sensors that you can be calibrated so that the values you're looking at compare favorably to one another. If you're using multiple sensors, you want to select bands that are as similar to one another as possible. Radiometric resolution. Ideally, you have the same radiometric precision on both dates. In other words, the accuracy at which you measure certain things are going to be constant. And spatially, you want the same instantaneous field of view, the same angles and all that sort of stuff, minimum map units, whatever. You want to have the same angles, so the registration of the individual images is kind of important, and it is a lengthy but necessary process at times to go through and make sure you register those images again. So even though they're geo-referenced, you want to make sure that the elements within image A and image B line up perfectly. So let's look at radiometric resolution just a little bit more. Radiometric resolution refers to how much information is in a pixel, and it's expressed in terms of bits. So we have a single bit, that's a 1 or 0, yes or no kind of thing. Black and white data is typically 8 bits, which means it's on a grayscale between 0 and 255. Now if we're talking about a color image where we have 3 channels, then they're 8 bits apiece, each color on a scale of 0 to 255, for a total of 24 bits. And so that's what you would have for color. So you don't want to be comparing a color image to a black and white image necessarily, because that's a significant change in terms of the radiometric resolution, and that can create issues. So for example, if the pixel value in the blue chip channel is 255, that means that pixel is bright blue. So if a blue channel has a radiometric resolution of 8 bits, there are 256 shades of blue. If it's 12-bit, then there's literally 4,096 shades of blue. And if there's 14 bits, it's 16,000 shades of blue. So, how blue is the blue? Radiometric resolution can make that not such an easy thing to answer. Okay, so let's look at how remotely sensed data used for change detection should be geometrically rectified. Because it all needs to fit and align perfectly, or as near to perfectly as possible. So why do we rectify? Because we want things to line up. To detect change, you must align exact locations with each other. You need to make sure the difference is a change and not a poor registration. So when we talk about remote sensing considerations of importance when conducting change detection, what are we talking about? Failure to understand the impacts of various environmental characteristics on the remote sensing change detection process can lead to inaccurate results. When you perform change detection, it is desirable to hold as many variables constant as possible. The less that's going on, the easier it is to see the change. Things like soil moisture. If one image is wet, one image is dry, you will have a noticeable different color, and you'll have a noticeable different response in the near infrared. Conditions should be identical for every date that when you use images as far as change detection. Vegetation phenology. What does that mean? That means vegetation grows according to relatively predictable diurnal, seasonal, and annual phenological cycles. Trees sprout out in the spring, turn green, grow all summer. They flower, they make nuts or fruits or berries or whatever they do, and then come the fall, the leaves change color and they fall to the ground and the tree lies dormant until spring, when it buds out and starts over again, unless of course it's an evergreen, in which case it loses some of its needles periodically. But the tree itself remains green. For example, if you've ever had a magnolia tree and you live just a little too far north for magnolias, you will get significant damage from frost and winter freeze on some of the leaves. And it can make a magnolia tree look quite unappealing for a while, because the damaged leaves, not completely damaged, but maybe half the leaf or part of the leaf has been burned away by the freeze or the frost, doesn't fall off the tree right away. The life expectancy of a leaf on a magnolia tree is something like 3 years. And so in any given year, you lose about a third of the leaves. Here's the thing though. The ones that damaged, are they scattered across all of the different years, or just the new, or just the old? So you might have a lot of frost damage one year, and then that following fall, all those leaves fall off, or it might be that only a third of them do, or somewhere in between. Okay, so here is an example of some soil, and when we add some water to it, you see that it obviously changes color. But in certain frequencies, that color change would be even more pronounced because certain frequencies respond more favorably to water. And so you would get a very different spectral signature. So, significant changes in moisture changes the color of soil. More moisture changes response in some bands significantly. Specifically, infrared and near infrared. Why? Because they respond to water. And when that happens, it will look like a very different place, because it will have an altered spectral signature. So let's look at the vegetation and see how it can be affected by some of this stuff. Here's an example of a bunch of trees, and they all have different colors that they relate to, and this could be a fact of the different types of trees. It could also be a fact of the different time of the year. For example, in many tree species, when the leaves first come out, they are not dark green, they're a lighter color. It's only after they've been out for some time do the internal structures in the leaves fully develop and acquire that deeper, darker color. But still, some are never as dark as others, because some trees simply have darker leaves. But it's not just a matter of the leaves and how dark they are. Different types of trees have different types of leaves. Here we have a white pine. I think it's a white pine anyway. And you can see these needle structures, they respond very differently to moisture stress than what traditional tree leaves do. These trees are more adept to dealing with limited moisture because they're not as photoactive. They don't have that big area. They're smaller, they're waxier, they don't lose moisture. And so they're also thicker, and so they respond differently, have a very different spectral signature. But not every evergreen looks like a white pine. Some have more unique leaf structures, much like a cedar or an arborvitae. And still others have a similar needle-like structure, but a very different color. In this case, a blue Colorado spruce. So what does all that tell us about vegetation? Not all leaves are the same color, and not all trees respond the same. Not all evergreens are the same. and that the needle structures are different, and all of this responds changes to how moisture, misspelling there, I'm not going to change it, I'll leave it there for you guys to laugh at, or season could expose maybe a new species. For example, what if you have let's say a small shade tolerant species like maple or hickory that's invading in a rather large pine or coniferous sort of forest that can tolerate the shade, and they can do well. Certain times of the year you may not even be able to see one for the other, but when the evergreens are sitting there and the moisture level's low and the foliage on the understudy, the brushy undergrowth, the maple that's trying to develop, begins to lose its leaves, but before it loses it, they change color. It might be that you would get a very noticeable and unique spectral signature that would be very different, that you may not have noticed in regular imagery. So let's take a look at some of the different colors and things that we'll see in vegetation. So here's a nice example of a bunch of different leaves and different colors that you would see typically in the fall. We have an assortment of different types of maples here. I believe these are all maples. We've got some sugar maples, some mountain maples, we've got some red maple, some striped maple. I don't know the rest of them. Might be a couple oaks in there too. Can't promise you that. But what I do know for sure is they're all hardwoods. And as they change color and fall from the tree, they change colors differently. In this example, you see some are bright yellow and some are just a dull green, some turn a brilliant red, some turn an ugly brown, some turn a combination of two or more of these. And when they're on the ground, it's even harder to tell what they are. But if you understand the phenology and the way the vegetation works and the time and the season, and you collect data, in other words, you select images in the right time of year, you can, from the colors you see, learn a great deal. I'll give you some examples. Walnut trees, locust trees, their leaves turn early, they turn yellow, and they fall quickly. Maples provide much color. They're really bright, oranges and yellows. They're sort of in that next band of stuff. But they fall relatively easily. Oaks usually turn browns, and they usually hang on to the tree longer than the other leaves. So knowing this sort of recipe, if you know when the pictures are taken, you can, just by looking at what is there, get some idea of the types of trees. And by knowing that, you can also know whether it is an appropriate time frame to collect an image from to compare to an image from an earlier time for the purposes of change detection. So let's talk about what these algorithms are that actually do change detection. So change detection algorithms that are commonly used include post-classification comparison, multi-date composite image, principal component analysis, image algebra, or band differencing or band ratioing, and change vector analysis, as well as binary mask. So let's take a little bit of a stab at a couple of these. Post-classification comparison change detection requires the rectification and classification of each remotely sensed image. What does that mean? It means that in order to do change detection in this fashion, you have to apply some sort of a classification scheme to the image. So you don't use the raw image. You classify it out as this is this and this is this. And then once you do that, and the images are rectified, in other words lined up perfectly, and the classification has been completed, you can then compare one to the other and determine if there was a change. The two maps are compared on a pixel by pixel basis, and you use something called a change detection matrix. Every error in the individual data classification map will also be present in the final change detection map. So you want to make sure that your classification is as good as possible. Individual maps used in the post-classification change detection method must be as accurate as possible. So let's take a look at what we're kind of talking about here. For example, date 1, you've got bands 2, 3, and 4. They're rectified thematic mapper bands. You sort of combine that together, you get this classification map for date 1. Then you go over to date 2, you got images 2, 3, and 4. You rectify the thematic mapper bands to make sure everything lines up. You do a new classification at the second date, and you end up with the classification map of date number 2. You then bring down your date number 1, and then you do a change detection, and basically it uses this logic that says it should be the same in 1 as it is in 2, and it determines whether or not it is or it's not. So what are the advantages of something like this? It does not require atmospheric correction because we classify the image into basically categories, and we do the same thing on the other one. And once we have those categories, we compare category to category. So it provides from to change class information, and the next base year map is already complete. And so you have the date number 2, and when you want 3, you can go back to it. Now what's the big disadvantage? It is dependent on the accuracy of the individual date classifications, and requires 2 separate classifications. Screw up either one, results are no good. So let's look at what this kind of means. So here we have some imagery before and after Hurricane Katrina. This data was used in a tutorial or classified images created from land cover analysis produced by NOAA, and it uses this coastal change analysis program CCAP standards. It's at 30-meter resolution, and it's using the Landsat thematic mapper and the Landsat enhanced thematic mapper imagery, looking at these two areas. And what they've done is went over each of these and classified every land cover in each scenario. Now, what is the difference? Well, just looking at it cold here, I don't so much notice a great deal of difference, but I'm sure there probably is some. I'm just not sure where it's at. So how does that decision matrix work? You have the different classes: developed, exposed, cultivated, grassland, urban, estuary, river, what have you, in the before and in the after, and you simply compare what they are. And if it was developed and it is developed, then it should still be developed, right? If it was cultivated and it is cultivated, it should still be cultivated. And so on and so forth. And then from that they come up with the different numbers of classes of things that are what have you. And so when you look at the amount of cultivated land that was classified as developed, you get a value. Cultivated classified as cultivated, you get a value, etc., etc., etc. Now in this scenario, the pixels are just numbered out. It's not matching things up. But once you have this, you can kind of get some idea of how that matrix would work, and then you can look things up and figure out what's going on. So how do you go about selecting your change detection algorithm of choice? Well, common ones: post comparison, multi-date composite, principal component, image, algebra, vector analysis, binary mask. Not easy to figure out. Let's look at the multiple date composite image change detection. We've already looked at some of these a little bit in the past, but In this you have multiple dates, multiple bands. You apply the traditional classification and figure out the principal components. Doesn't require single classification. It does not normally require atmospheric correction. So requiring a single classification is an advantage. The disadvantage is difficult to label change classes, and there's little from to change class information, so you really can't compare it so much. In order to do this, you got to rectify multiple data sets of imagery. This composite data set can be analyzed to extract the change information. Unsupervised classification techniques will result in the creation of change and no change clusters. The analyst must then label the clusters accordingly. So let's look at some multiple date composite image change detection based on principal component analysis. And so we've got principal component 1s, 2 and 3, 4, 5 and 6, and you're trying to find what's going on. In this example, principal component 2 is a good indicator of change in time. You get to see the white areas, which are the areas that are dramatically different. Let's talk a little bit about image algebra change detection. You identify change between two rectified images by band rationing, band ratioing, and image differencing. Image differencing involves subtracting the imagery of one date from that of another. The two images have almost identical radiometric characteristics. This works fine. The subtraction will give you either a positive or a negative in the areas that there has been change, and zeros in areas that have not changed. And then you can get this result stored in this new change image. And let's see what that would kind of look like. Change detection, date 1, date 2. Get a composite. You can do a band differencing. And then you can figure out change, no change. So this is a slightly different variation of what we were looking at earlier. You have the two dates, and you can create a composite data set for each date, and then figure out how they differ from one to the other. For example, red, green, blue, or false color infrared, false color infrared. Then you compare those final composite outputs to each other, and you look for, why is my red different? Where is my green different? What have you. The threshold to produce change, no change is something you kind of got to come up with. What are the advantages? Does not require an atmospheric correction. It's an efficient method for identifying pixels that have been changed in brightness values between dates. Disadvantages, there's no to from stuff, and it requires a careful selection of that change, no change threshold. In other words, how much difference is difference. And so when we talk about the difference of the band ratioed image, band ratios are when you, for example, divide your near infrared by your red. Whereas differenced would be if you, for example, subtracted your values in one from the other. So let's look at image differencing, change detection, scaling alternatives, and the placement of user-specific thresholds in a change image histogram. Well, that's a lot going on there. So here's basically what we're saying. Pixels that don't change much between dates have a mean that is often displayed as 0, and that should be the most of the pixels. Some have a little bit of change. If you think about a normal distribution, there is a point where you say, you know what, that change is significantly different than 0, either positively or negative, and that occurs out on the tails of the distribution, and that's kind of the areas that we say, hey, something actually changed. It got lighter or it got darker. So we've talked, or I've mentioned, or I've stated, or I've said the words principal component analysis a couple of times. So I want to talk a little bit about that, how it works. Principal components tool is used to transform the data from an input band from the input multivariate attribute space to a new multivariate attribute space whose axes are rotated with respect to the original space. These axes, or attributes, in the new space are uncorrelated. The main reason to transform the data in a principal component analysis is to compress the data by eliminating redundancy. Well, that says a lot, doesn't it? What does it mean? Well, you try to find that thing that explains the most amount of variability in your data. If you think of your data like in a three-dimensional cloud, imagine it as an arrow that passes through the cloud that identifies the most possible difference. Now what's left are these residuals. What you're then shooting for is another variable that explains the remaining difference, but not one that goes in the same direction as the first one, but one that goes orthogonal to the first one. So for example, if we just think of it in two-dimensional space, if the first variable, the first component, is right down the 0 x-axis, then right across the 0 y-axis would be orthogonal to that. And so one to the other, and the idea being that by finding these orthogonal kind of different components that explain the remainder of the residuals, what you're getting is things that aren't correlated. And so each component explains as much of the variability as it can, and then the remaining variability can be assessed to determine if there is something that will explain that variability on its own. That's more or less how it works. So an example of data redundancy is evident in a multiband raster comprising elevation, slope, and aspect on a continuous scale. Slope and aspect are usually derived from elevation. So when we have that, most of the variance in the study can be explained by just the elevation data. And so the other two elements are collinear, highly coordinated with, similar, comprised from, made by, out of the other. So the results of the tool is a multiband raster with the same number of bands as a specified number of components. You want 3, it gives you 3. 1 band per axis, or 1 component in the new multivariate space. In this new space, you get the first one. It's the component that has the greatest variance. The second one is the second most, and so on and so forth. Alright, so many times the first 3 or 4 rasters of the resulting multiband raster from principal component will describe 95% of the variance or more. The remaining bands are often dropped, and since the new multiband raster contains fewer bands, more than 95% of the variance of the original is intact, and the computations will be faster and the accuracy can be maintained. Principal components require the input bands to be identified, the number of principal components into which to transform the data, the name of the statistics, the output file, and all these other things. The output raster will contain the sample numbers of the bands and the specified number of components, and each band will depict an individual component. Now, I'm sure at this point we all understand this perfectly, right? Well, let's see if we can kind of maybe draw this out a tick with some illustrations. Maybe it'll make a little more sense. Got a bunch of data. The data is plotted in a scatter plot. If you do an ellipse, it's calculated to bound the points in the scatter plot. The major axis is determined. In other words, so this is the cluster of the data, and we figure out that axis that goes through it. That axis, whatever the variable is that explains that, or the model that we come up with that explains that, that is our principal component number 1. It's a variable that we make, a new variable, in multivariate space, made up of all the other variables that we had. Okay? Then we go orthogonal, like I said, perpendicular to that first one. That explains whatever's left. And this is a new combination of our original data fields that we had that can be put together to explain the most of that. And so each one explains more and more. Another type of change detection I want to talk about is cut and fill, or mountaintop removal. This is literally where we take elevation data and we use it to calculate elevation change detection. So if we take a digital elevation model from 2 different time periods in an area where we know there's been serious excavation work, we can use map algebra. Using the pre and post, we can identify on a pixel by pixel basis if the elevation has increased or decreased. Where it has decreased, we know that is a removal, and where it is increased, that is a fill. So, positive value, valley fill; negative value, mountaintop removal.